Hello, community. Can you trust vision language model? Is there an intelligence into the vision reasoning or the visual thinking capabilities of AI currently? Let's have a look. We have two new research papers from Harvard and Princeton. So at first, the idea is simple, no? Kind of a new communication modality, no? What we have a numerical data stream, pure data in itself. Then we have another representation. This is code in Python, C++. Here, if you want, here we define here a sequence of operation in the code. And then, of course, we have a linguistic semantic representation of our ideas in an English text. So if we provide this to an AI, could we do any better? What about we provide now a data visualization given here a very particular perspective in a specific high-dimensional vector space? Would this help? Would it help, for example, if it sees that there is a data clustering happening or any other algorithm, any other operator on the data? So, idea, simple. Can we design visuals of any kind of complexity to help our pattern matching machine, our AI agent, to perform a task, to become more intelligent, to increase its reasoning performance? And we are working here now with multi-modal AI system or multi-modal agents, so we have to take care about this. And the authors here, easy, they said we take two leading VLMs, well, not so leading anymore. We have 3 common data analysis tasks that we examine, and we have 5 different input conditions that we carefully select because we want to isolate here the visual thinking process from the semantic linguistic thinking process of an LLM. And to be statistically relevant, we do 12,000 individual runs. Great. So these are the two grandfather vision language model, a GPT 4.1 and a Claude 3.5 Sonnet. And if you say why they take this old, yeah, imagine they would take a current vision language model and show that it has some malfunctions or some errors or some faults in visual reasoning. Come on, no university would dare to do this to a global corporation where this corporation might give here a donation or even has here a career path forward for their students. So we go here with grandfather models. So wherever we run the models, we simply give them a prompt. And this is kind of beautiful because it's so simple. Have a look. What are the patterns, the trends, and the features of interest in the following data? Nothing else. Let the vision language model do its thinking. And then we have 3 data analysis tasks. Couldn't be easier. Detect a cluster. My goodness. Have a parabolic trend identification. Easy. Or the simplest one, an outlier detection. You have 50 points and 1 point is off this particular line, shifted on the z-axis. That's it. That's the complexity. But to isolate now the effect of the visualization, thinking of the reasoning in the visualization, if you want hyperplane, they had a beautiful idea. They say, okay, at first we give the data stream only, this is the baseline, no? Numerical raw data, X, Y, Z data. Then, because we are doing here multimodal reasoning, we just give it a white image with no visualization at all. Just to make sure, if we switch here to a multimodal reasoning, does this has any effect on the model? And then we say in control group 2, the data and the wrong visualization. Do we have any effect if I give the right data and a wrong visualization to the eye? What would happen now? And then, of course, we have to give 2 correct visualizations, a data and a correct visualization, so both the raw data and a correct scatter plot of the data, for example, in any dimension you like. And then, interestingly, only the scatter plot, no raw numerical data. So this is now isolates, if you want, the power of the visual information alone. So here we really test here from the vision language model, what can it detect here on the visual channel alone. Now there's a lot of interesting data in the paper, in the preprint, please read it. I jump to the evaluation methodology and the result. How we evaluate? Now for a parabolic task, easy, no? Simply a keyword search if it's the answer includes the word parabolic or quadratic complexity. And for clustering and outlier tasks, guess what? We go with a Gemini AI system as an automated AI judge. So AI judges AI. And here we have another study. Harvard University and Google Research published July 24, 2025. Does additional visualization help our vision language model to understand the data and have a better reasoning process or a better thinking process on the data going forward? Just think about financial domain tasks, how you could improve here the financial understanding of an AI if this would work. Let's go to the result. Simply, yes, it works, but since it's done by Harvard, they had some special questions and some deeper insights, and I think this is what makes the study so elegant. So at first they noticed that the data and the wrong condition, the visual condition, produces here the worst performance, even worse than just providing here the data alone. So this is a critical finding because this means that AI, like people, are really sensitive to actively being misled by some visualization that do not correspond with the data. The AI has not learned what to do if this is the case. So we have to improve the pre-training. Second, if you look at this, does the VLM tell us, hey, I have no idea because I suddenly detected I have here some data stream, numerical data, and then I have some visualization, and it doesn't go together. This is a discrepancy here. No? The AI said nothing. Only in 7 times out of 800, it dared to mention this. So the AI stays silent and fails silently. Either it's so confused or trusting here the visual input over the numerical input, we have no idea. It's a black box. Both systems. And then they looked at a comparison between the data and correct visualization and correct only one. And they said, interesting. If it's about shape like the parabolic task, when the trend was very, very subtle, providing only the chart was more effective than providing the chart and the data. So this means making the global structure immediately apparent here to the model visual system was here the path to success. On the other hand, if we just went for identifying here a specific point, like in the outlier task, here we've seen that providing both the chart and the data was better than the chart alone. So here they are used, if you want, synergistic use here of both modalities. Interesting. So much depends on the pre-training data set. Now, let's look here at some visualization itself. Yes, I know it's a joker in itself. So here we have GPT-1 on top and Claude 3.5 Sonnet here on the bottom graph. And as you can see, if you look at this, if we increase the number of clusters here, GPT, you see, we have a beautiful performance here of the data and the correct visualization and only the correct data. It works. It simply works. Everything else goes down with the number of clusters, with an increased complexity. And the same is true for Claude 3.5. We start with perfect configuration, but then look, it immediately goes down just with 3 clusters, 4 clusters, 5 clusters. The data and the wrong visualization is horrible. It has almost no identification at all. But the data and the correct only version, yes, they stay at about 70-80%. Great. GPT 4.1 is a little bit better, as you can see. So what does it mean? This is the clearest visual proof that providing here the correct visualization dramatically improves the performance over the data-only baseline. So inserting here this new communication representation of a visualization helps the AI in reasoning and detection, and if you want, thinking. Now let's have a look here if we go here for the parabolic test. Now this is now kind of interesting. Huh? You see that the correct only bar is significantly higher than the data and the correct bar. Let's go here with Claude 3.5. Ne? Correct only or the data and the correct. So this supports now the argumentation for the task involving here a faint global pattern. The raw data can act as a noise, and the visual alone is the purest signal. So here in the dark blue, you have here the visualization only. And even if you give the raw numerical data and the correct visualization, the performance decreases significantly. Look at this. Unbelievable. Why is this happening? And of course, and I think this is absolutely fascinating, they looked here at the output token count. How many tokens were produced here for the output? Representative output token counts on the outlier detection setting. So we go here with this test. And the correct only option here produces here the shortest. This is here the dark blue if you want here, as you see both. Careful, the y-axis is not identical here for GPT 4.1 and Claude 3.5. You have here 800 tokens and here you have only 300 tokens. So this is now here an argument that says when presented with a visual, the model kind of shifts its internal reasoning strategy. So instead of performing now some broad statistical computation or maybe just some estimation, the model now hones in on a most salient visual feature and reports this directly. So if you want, this is a kind of a behavioral signature of a shift from a statistical analysis mode to a visual pattern recognition mode. So suddenly the model switches here from statistical analysis to really visual pattern. Interesting when an LLM or a vision language model decides to have an internal strategy switch or a mode switch. It depends heavily on the vision language model, the model that you use. But in general, let's say we can have proven now that the visualization is really kind of a powerful tool for enhancing the AI data analysis. So you might say, hey, this is great. And the authors Howard had some question, in which scenarios is the visualization the most beneficial? Or where should now in the complete processing pipeline the visual be introduced now exactly in the data pipeline? Where should we provide this additional, if you want, optical perspective, a visualization of a particular, not of a polarization, but of a particular data representation with a filter, a graphical filter, a geometric filter? And what are the underlying cognitive mechanisms to allow the visuals to help the AI? And how can we design and optimize specific visualization here for an AI multi-agent audience? So you see, okay, great. First paper, absolutely, yeah. Shows that we can get better result from our AI analyst by pre-processing the data into a format that our LLM's visual system find helpful, intuitive, like a scatter plot. Great way to see clusters. And you might say this is a win for the human-AI interaction on the workflow design because we can now fuse together here linguistic and vision pattern recognition. Great. But you know, there's this little voice here in your mind that said, why did he mention the visual pattern recognition mode so explicitly? And why did he mention that there's the first paper? Yes, because we have a second paper from Princeton. Now, this is a little bit older here from the beginning of July 2025. And they tell us, Princeton, yeah, you know, vision language model have a tunnel vision. So we are now evaluating with Princeton University kind of a contrapoint to the first preprint. We are now evaluating non-local visual reasoning in leading VLMs. And finally, we don't go with grandfather models, but we go with a little bit better, Gemini 2.5 Pro. We go with the actual models. You see, Princeton has no problem with going with actual models. So, the first preprint we looked at in this video delivered here quite of an optimistic message. Now, visualizing data, in particular filtered representation, helps an AI, a vision language model, just like it helps human if you have the numerical data stream and a representation. Now, the second preprint here comes in with a bucket of cold analytical water. So guess what? Today's leading VLMs lack non-local vision reasoning. The fundamental ability to chain together information from different, sometimes distant parts of an image to complete a task is almost missing in modern vision language model. And you might say, oh, great. We are back here to something is not working. Yes, absolutely. We want to learn from failures. We want to get better. We don't just want to trust global corporation when they tell us in their marketing brochures, hey, this is the best model you can buy. So this preprint now shifts the focus from what a vision language model sees to how does it see this. Absolutely interesting. Think about it here in a simple analogon. It's the difference between recognizing here a city on a map to being able to trace a route through this particular city. So let's start. The authors here, Princeton, break down the complex idea of a visual reasoning in three particular, really specific defined tasks. Comparing things, searching for a sequence of clues, and tracing a path in a visual complexity. Nothing easier. We do this every day. So this provides a kind of a new, more rigorous vocabulary for diagnosing your vision language model weaknesses. And here we have it. Object re-identification, this visual scavenger hunt, and the circuit connection. And I will explain everything in detail. It's so easy, you're gonna laugh about it. The findings imply a fundamental limitation in our current vision language model architectures. Their success relies on the large language model text-based reasoning powers after performing independent glances at the image. So we are back to the LLMs, the linguistic model. The reasoning is not happening in the visual space. The reasoning is almost happening only in the linguistic semantic space. And you say, damn, I wanted to go multimodal. I don't want to transfer everything back to linguistic semantic complexity patterns. I want to have the freedom to go here in a visual language space and argue and counteract over there. So, VLMs struggle when the reasoning must happen in the visual domain itself. Great. So they developed also 3 core non-local visual skills. We have to prove this, no? So we have some comparative perception, the ability to hold a visual entity, like a cube or whatever, in a working memory and compare it to another, even under transformation. So you rotate in your mind the cube 90 degree, 180 degree, you change the color, whatever. You can do this as a human. Saccadic search. This is now the ability to perform some discrete evidence-driven jumps of the attention across an image. You go from the left corner to the right corner, from the right corner to the middle, and then from the middle you have an indicator or a vector go somewhere else in the image. You just jump around. And then, of course, we go from discrete to continuous tracing here a contour or a path in an image. So we talk about a smooth visual search algorithm. And we have variants, no? Standard, unconnected objects. So an object is here a constellation of disconnected shapes that transform together. And we have here a pixel perfect variant with a control here. A yes answer means the image 2 is a pixel 4 pixel match of image 1 under transformation, rotation, whatever you have. So the model is now shown a grid of colored shape where each shape is labeled with a text specifying here another object, another color shape pairs. So for example, as I've shown you, you have here the teal triangle has the text on it that says pink circle. And now your job is to go to the pink circle. So as a vision language model, you have now to do here something that is not as simple, because this is an iterative process. No, you go find shape A, read the label on shape A, then you find the shape B with the characteristics of the label, then you read its label, and then you continue on. So the reasoning is inherently sequential and visual. So you need both. And this is here this, yeah? Find a sequence. Start somewhere. Tell me after 3 steps, where are you? Easy. You can do this at home. So what are the results? Just give you the insights. Read the paper yourself. You're gonna love half the way. Insight 1. Models can't compare coherent objects at all. Great. So here you have it. Object re-identification after you rotate it or have a translation or whatever. So here we have our models. And you see here at 50 is here random chance. You know, this is you flip a coin, this is it. And this is where almost all the models live. Maybe you could argue that here with a Gemini 2.5 Pro with 65, you're a little bit better. Or here with a OpenAI 04 Mini, you're a little bit better here. But for the rest of the bunch, I would say, If you go with any other model, then here really those two, and maybe O3 is with 55, a little tiny bit above random, but I would say, hey, it's not worth spending any money on this, yeah? So on the standard object re-identification task, even the best VLMs and the most expensive VLMs perform barely above random, above the 50. So they could not reliably tell if a coherent object was the same after a simple rotation. And you say, wow, great, this is what I pay for. And look, for human, it's easy, no? You can do this in your mind. You don't even have to see it on a computer screen, no? Now, the shocking twist is the performance improves significantly on the unconnected and on the pixel-perfect variants. What does this mean? This means that the models have a strong but flawed priors in its internal understanding, quotation mark, about what constitutes an object. So when faced with a coherent shape, their internal models, do you remember the internal world models we were talking about in the internal reward systems? Their internal models, what is an object, get confused by the transformation. They can't identify it anymore. But when the object is just a loose collection of parts, 1, 2, 3, they are better at comparing the individual simplified pieces. So this means now they can handle single parts, but they cannot handle the whole object itself. Again, reduce the complexity. AI has no chance if it has a higher complexity than the standard geometric forms. Insight number 2. Models don't search, they just guess. And you say, hey, that's great, this is why I pay for my AI system, no? Saccadic search failure. What does it mean? Look at this. Here again with 9%, this is the random chance, yeah? And you see 90% of our vision language model, you say, hey, wow, great, no? 7B, 11B, 32B, oh wow, beautiful, yeah? If my Claude 3.7 Sonnet would say, not at all, yeah? Maybe an O4 Mini or a Gemini 2.5 Pro. O3, no, not really, yeah? Human, 100% easy. So what is so easy for humans, even the best Gemini 2.5 Pros, yeah, they are better than the rest, yeah, but I don't know how many GPUs you have to activate in the cloud to get this result. So for a local AI implementation on a local laptop or a home computer or whatever, if you go with a Claude 3.7 Sonnet, no chance at all for visual scavenger hunts. But the performance didn't consistently decrease as the chain length grew. So this indicates they weren't even attempting here to go here the sequential algorithm along. Instead, they were simply using a heuristic, like guessing here the most frequent color in a particular image. So they couldn't execute a simple visual program like follow the trace. They failed. They just went with a color identification. And now let's come to insight 3, because we want to finish this video. This gets depressing here. And people are talking about super intelligence. It's just a joke. Insight number 3, models don't trace. They just match colors. So let's make it even more horrible. So even the smooth visual search is a complete failure with the best vision language models. Now the gradient proofs, and please have a look yourself at the paper, that the vision language model are not actually tracing here the wires that I showed you here as the third exercise. They are relying almost entirely on a color matching heuristic scheme, but not following the path along. So when this shortcut is taken away, if you have everything now in a single color, the ability of the vision language model to solve now this particular task collapses completely. Great. But you know, you might be a little bit depressed, as I am currently now. But this is to improve the next generation of models. We have to understand what is working, what is not working at all. And then we have to go back to the drawing board. We have to intensify the pre-training of the vision language model. We have to start all over again and improve. Yeah, if you want to see here from the original publication, you guessed it. Great. So what is the summary of both papers? Now, both papers are interesting together, and I selected those two papers. Also, they are 3 weeks apart for a particular reason. They absolutely are a counterpoint to itself. So on the one hand, we say, yeah, visualization are great. This is another data representation that we find here to help here the AI, vision language model, to have here, if you want, a reasoning process in the visual domain. So in the first paper, we asked, does changing the input modality from pure numbers, numerical data streams, to a visual representation improve the performance of a vision language model? And I think the answer is yes, with limitation, but in general, yes, it helps. Now, in the second paper, the question was, can vision language model perform sequential reasoning algorithm within the visual modality itself? And the answer is an absolute no, no way. The benefit of the first paper, if you think about it, comes from how the data is represented in another representation space in addition to the raw data to the vision language model. So interesting. However, the failure of vision language models, its inability to process that visual data sequentially, even in a single static image. I'm not talking about video, I'm talking about a static image. This failure is in the VLM itself. So I think this reveals here the, if we call it the layered nature of our vision language capabilities. No? So we can help those systems by giving them an additional visual data representation, a particular polarized filter, a particular summarization, a particular cluster algorithm, a particular, Fourier analysis. So we can help that the AI understands here the hidden patterns in the data stream. But we must be aware that the ability to reason about those images or this visualization is currently wide, but incredibly shallow, almost non-existent shallow. So this vision language model can see the forest on an image, but they have no idea how to follow a path through the forest. Not at all. Okay, this is the video of today. I'm a little bit disappointed reading here the latest AI research papers because, here in the marketing and on all the social media platforms, you see, yes, super intelligence is coming next week. And you know what is the reality if you really have an analytical process where you analyze the performance step by step? The reality is, yes.